Okay, let's go ahead and get started. So this is the last lecture, and I thought what I would do today is simultaneously describe both the high point, I think, of the theory of quantum electrodynamics, namely the computation of the anomalous magnetic moment of the electron. And this will also serve as a bit of an introduction to some of the things that we'll be discussing next semester when we talk about renormalization, counter terms, effective field theories, and sort of the structures of quantum field theories more generally. But in particular today, what I want to focus on is a particular correction to the dynamics of electrons in quantum electrodynamics that I think stands as probably the most important result in quantum field theory, one of the most important results in physics, and I believe still stands as the single greatest check between a theory and experiment in the history of physics. Okay. So let me just begin with a sort of schematic introduction to what we're going to be discussing today. So what I'd like to do is consider corrections to the interactions between an electron and a photon. So in particular, I remind you that in quantum electrodynamics, the way that we describe an electron interacting with a photon is through an interaction vertex that looks like this. So this describes an electron interacting with a photon. So what we want to do is imagine more generally processes that could occur in quantum electrodynamics where you have one photon coming in that is interacting with, say, an electron and a positron, or an incoming electron and an outgoing electron. So in quantum electrodynamics, you could imagine the sum of all possible diagrams with one external photon and two external electrons, which I've denoted just by sticking a blob in there. And of course, at leading order, in the coupling constant, this would just be given by the usual interaction vertex. But then there would be a lot of correction terms involving the addition of more interaction vertices, loops, and so forth. Okay? And so what I'd like to do is I'd like to consider the sum of all possible diagrams like this, and think of this as including all possible corrections to the usual traditional interaction vertex that describes an electron interacting with a photon. Okay? And if I had just that single interaction vertex, the tree-level interaction vertex here, what this would be is this would be minus IE times gamma mu, the Dirac matrix. So in general, I'm just going to give a name to the sum of all possible diagrams. I'll call it capital gamma mu. And this will be a function of the ingoing and outgoing momenta of the electrons, as well as the momentum of the external photon. But of course, by momentum conservation, Q is equal to P minus P prime. So I could just regard this matrix capital gamma as a function of P and P prime. So this is the full quantum vertex. That is to say, it describes the interaction between an electron and a photon, including all possible quantum corrections. Okay. So in particular, you know that gamma, well, at leading order, it's just given by gamma mu, but then it'll have various corrections that are higher order in the coupling constant, and in particular, as we'll compute later on in class today, they'll look like order E squared, so order fine structure constant, plus terms that are even higher order, fine structure constant squared, and so on and so forth. But before we get into the detailed computation of these terms, I thought we could just spend a minute thinking about what on general grounds these various contributions to the quantum vertex could look like. So in particular, what do we know? We know that this matrix gamma, so I should really put an index there. Well, what is it? It's a 4-vector, but it's also a spinor matrix. It's a 4x4 spinor matrix, so it's really a set of 64 quantities because it has a 4-vector index as well as 2 spinor indices. But whatever it is, you know that it must be built out of only a certain set of quantities. So in particular, it involves, or that is to say, it is built out only of, say, the mass of the electron, the electric charge E, as well as the various momenta P, P prime, and Q. And of course, we don't need to write Q separately because it's just P minus P prime, as well as this gamma matrix. And just on general grounds, those are the only quantities that enter the problem, so the answer must be a function of those. And if you think about it, there are only 3 possible 4 vectors that you could build out of these quantities. So gamma mu is a 4-vector. So the vertex could be gamma mu times some 4x4 Dirac spinor matrix A. Or p mu is another 4-vector. And p mu prime is another 4-vector. And so to make life simple, I'll use the following linear combinations: p mu plus p mu prime and p mu minus p mu prime. And just on general grounds, because these are the only 3 4-vectors that are present in the problem, the general form of the quantum vertex must be a linear combination of those 3, where A, B, and C are 4x4 Dirac spinor matrices. Well, they could also be constants. So for example, the identity matrix is an example of a 4x4 Dirac matrix. But in general, remember that these P's and P primes carry spinor indices. Okay. So in general, they could be Dirac matrices.
So gamma mu is already
Gamma mu is already a Dirac matrix. Okay.
Oh, okay.
Yeah. But it could, yeah. But it could be multiplied by some other Dirac matrices, for example. Okay. However, it turns out that we don't really need to worry about the Dirac nature of those arbitrary functions A, B, and C, because in any scattering process, this quantum vertex will be contracted with some external spinors. So that is to say, some external spinors describing the polarizations of the external electrons or positrons. So in particular, the sort of terms that would arise will all involve things like, so what did we call this? We call this P prime and this P. So the only sort of terms that will arise are things like U bar of P prime, gamma mu, U of P. Okay. And I suppose there should be a minus IE here. Okay. So U of P prime, U bar of P prime is the polarization here of the outgoing electron. U of P is the polarization of the incoming electron. And I remind you that the polarization U obeys an equation. So P slash of U is equal to mu, right? That's the Dirac equation written in momentum space. And similarly, when acting as a 4x4 matrix from the right, U bar P slash is equal just to U bar times M. So what does this mean? So this means that if you think about the Dirac matrices that could enter into A, B, and C, you ask yourself, what sort of Dirac matrices could you build out of these quantities? Well, you could build P slash and P slash prime. Those are the only Dirac matrices that you could build. But whenever you contract them, whenever you multiply them with these external spinors, these external polarizations, those P slashes just turn into M's. Okay. So that means that we can effectively write A, B, and C as numbers rather than Dirac matrices. That is to say, A, B, and C are scalars and are functions only of these quantities here, M, E, P, and P prime. And in fact, if you imagine that you have external electrons or positrons that obey the equation of motion, P squared equals to M squared, you see that indeed they can't actually depend on P and P prime independently, because they only will depend on P minus P prime, because P, or rather, or how should I say this? They will only depend on M, E, and Q, right? Because P plus, right? Let me put it a different way. They're scalars, and the only scalars that you can build out of M, E, P, and P prime can be built out of M, E, and Q. Just because Q squared is P minus P prime squared, and that differs from P plus P prime squared only by N squared. Or, sorry, I didn't say that. Maybe the best way of saying that is that the only scalars that you can build out of these quantities are M, E, P squared, which is M squared, P prime squared, which is M squared, and P dot P prime. And so I could just as well write, instead of P dot P prime, I could write Q squared. Okay. Good. That's probably the best way of saying it. Okay. So you have these three scalar functions, A, B, and C, that can appear in the general quantum vertex. And there's one more piece of physics that we need to include in order to understand what kind of functions can appear here, which is something that we learned about last week, which is the Ward identity. Remember, the Ward identity is a consequence of gauge invariance, and it tells you that whenever you have a scattering amplitude with an external photon, that scattering amplitude contracted with the form momentum of that photon must be equal to 0. In this case, that means that gamma mu contracted with q mu is equal to 0. And you can see here, what is this? This guy is q mu. So that tells us that that function c is equal to 0. Because if you work it out, if you contracted this guy with q mu, you would get 0. And if you contracted this guy with q mu, you would also get 0. But if you contract this guy with q mu, in general, you need to set c equals to 0. There's actually a little bit of a subtlety here. If the photon is on shell so that q squared is equal to 0, then, well, there's nothing to say there because q squared is equal to 0. But the photon that you're contracting it with here doesn't necessarily need to be on shell. It could be some sort of internal photon. For example, if you were studying electron-electron scattering, then that photon would not necessarily be on shell. It would be some virtual photon. Q squared would not be 0. And the only way that this could be consistent with the Ward identity would be if c is equal to 0. Indeed, one can actually do an explicit computation and check quite explicitly that c is equal to 0. In fact, when we go ahead and compute this quantity at loop level in quantum electrodynamics, we'll be able to see explicitly that c is equal to 0. Okay. There's one final simplification I want to make. It's not really a simplification as much as it is a notation. But what I want to do is I want to use what's known as the Gordon identity, which is just a straightforward identity for spinors. In fact, I believe I made you prove this, or at least a version of this on a problem set. I made you prove a simple version of it, I think. Basically, the Gordon identity is just some equation that you can derive by manipulating the Clifford algebra. It's just a consequence of the Clifford algebra. And it says that if you sandwich a gamma matrix between two polarizations that solve the Dirac equation, then you get p mu plus p mu prime over 2m plus I sigma mu nu q nu, where q nu is p nu minus p nu prime over 2m times u of p, where sigma mu nu is the commutator between two gamma matrices, which is the generator of a Lorentz boost in the Dirac representation. So remember, these sigma mu nus, I might have called them J mu nus when we constructed the spinor representations of the Lorentz group, but they're the commutators of gamma mu and gamma nu, and they're the things that obey the Lorentz algebra and describe the transformations of spinors under a Lorentz transformation. So I believe in the problem set I set p equals to p prime, one of the early problem sets in the semester, and you didn't find this term, but you found this term. Okay. Does that ring a bell? Okay. I think you proved that on a problem set. And it's a simple generalization to prove this a little bit more generally, to get the Gordon identity, which I wrote down. Okay, so let's put this all together. So what this means is that the full quantum corrected electron vertex is a sum of two terms, one of which is gamma mu times an arbitrary function of q squared, and the next of which is proportional to sigma mu nu over 2m q nu times another function of q squared. So what have I done here? What I've done is I've just taken this equation up here. I've set that last term equal to 0. And I've used the fact that when I sandwich this between a u bar and a u, this p plus p prime that appears here gives you a factor of sigma mu nu times q nu, plus a contribution that I can absorb into the coefficient of gamma mu. Good. Okay. So what is this? What have we done here? Let me just stop here and summarize what we've done here. So what we're doing here is we're considering the quantum corrections to the interaction between an electron and a photon in quantum electrodynamics. And we've packaged our ignorance into two unknown functions that I've called f1 and f2. And they're just two scalar functions that are a function of p1 minus p2, okay, or which I've called q here. That's the momentum of the external photon. So all of our ignorance of the full interactions between these particles and electron are packaged into these two functions f. And these two functions f are very important, okay? Whenever you have an interaction between a charged particle and, say, a photon, you can package your ignorance of the interactions between that particle and the photon into these two functions, which are known as form factors. And what I'd like to do is spend a little bit of time before going ahead and computing these in quantum electrodynamics, talking a little bit more physically about what these form factors mean. form factors occur all over the place in particle physics. They really capture the, so for example, what they're doing here is they're capturing all of the quantum structure of the electron as viewed by a photon in quantum electrodynamics. They appear all the time in nuclear physics, for example, where they would be used to describe the microscopic structure of a nucleon when it interacts with electromagnetism. They're used all over the place. So I think it's worth spending a little bit of time thinking physically about what they mean. Before I do so, let me just pause here and see if there are any questions. Okay. So I'm going to spend maybe the next 20 minutes talking about physically what they mean, how you would measure them, and then I'll talk about the computation of one of these form factors in quantum electrodynamics. Is the general strategy clear here? Any questions? So if you've studied particle physics, you've probably seen form factors before. I mean, they're kind of, in some sense, they're the essential pieces of data that enter when you want to try and describe, in general terms, the interaction of a particle with electromagnetism. Yes?
So-called Huygens scaling enters this kind of...
Yes, that's right.
Yeah.
Yeah. So there's a ton of physics wrapped up in these form factors. Okay? And they're really a packaging of our ignorance about the detailed structure of an interaction between an electron and a photon. So at leading order, in quantum electrodynamics, what do we have? The first form factor is 1, and the second form factor is 0. Okay. And what we're going to do is compute these quantum mechanically, working to next order in the fine structure constant, okay. The first quantum correction. But before I do so, let's just discuss a little bit what they mean physically. So let's just first think about that first form factor, F1 of q squared.
Is that 0 or?
I'm sorry, F2 is 0. Sorry about that. Good. So let's think about F1 of q squared. So what is F1 of q squared? Well, remember, the thing in the interaction vertex, you'll get a factor of minus IE times gamma mu. So if you imagine that you had, say, let's say that we had, I don't know, a proton here, and then you were scattering an electron off of a proton, so this is an electron, then at leading order, the way that you would describe that scattering is through a process like this. But then, if you were working at higher order, you would sum over all possible diagrams that looked like that. And so what you can see here is that if you had some F1 that is non-trivial, that's not just equal to 1, that would look like some sort of correction to the electric charge. And in particular, what you see here is that on general grounds, F1 could be a function of q squared. Okay. So what does that mean? That means that it's some sort of momentum-dependent correction to the electric charge. So for example, at q squared equals to 0, if you studied very low energy scattering or very long distance scattering between this electron and this proton, then you know that F1 just has to go to 1. To some extent, we define the electric charge, and this gets into the theory of renormalization, but to some extent we define the value of the electric charge E so that when q squared goes to 0, F1 is equal to 1. If you think about it, what would it mean if at q squared goes to 0, F1 goes to 2? Well, what that means is that there would be a correction to Coulomb's law by a factor of 2, and so we would just absorb that into what we mean by the electric charge. But, so you can imagine that at very low energies, that is to say at very, very long distances, you're looking at the interaction between this proton and this electron via the exchange of a photon. And as you crank up the energy, you can see that the effective value of the electric charge changes. So in particular, you can see that effectively the interaction between the electron and the proton can become either stronger or weaker depending on whether F1 of q squared either increases or decreases as q squared increases. So this is some sort of quantum mechanical correction to the electric charge as a function of the energy at which you study the process. So at very long distances, the electric charge is just E. It's the thing that you measure. Okay, it's the thing that you put into Coulomb's law. But then as you study very high energy scattering, you're probing Coulomb interactions at shorter and shorter distances. And this F1 characterizes the way that the effective electric charge depends on distance. And intuitively, you can understand how it is that the effective value of the electric charge will increase as you go to shorter and shorter distances. Roughly speaking, one way of thinking about that is that you think about, say, your proton here. So there's your proton. And then you think about, well, one of the things that you know about quantum electrodynamics is that you can have virtual positron-electron pairs. Okay? And so you could imagine, at least very heuristically, that let's say you have a proton which has a positive charge. Well, you could imagine that this charge gets screened quantum mechanically by virtual pairs of electrons and positrons. Okay. And that if you're and that what we measure as the effective charge of a proton incorporates the fact that there's a lot of this screening. But as you study the theory at higher and higher energies, that is to say at shorter and shorter distances, there are few of these virtual electron-positron pairs that will screen the charge of the proton, and so the effective Coulomb interaction will increase. So intuitively, that means that the effective value of the electric charge will increase as you increase q squared. Indeed, although the fine structure constant is 1 over 137 at long distances, if you look at LHC energies, the effective value of the fine structure constant is not 1 over 137. I forget what it is. It's like 1 over 120 or 110 or something like that. Okay, so this first form factor describes the way that the effective charge of the electron changes depending on the sort of experiment that you're performing. What about F2? So in order to think about F2, any questions on this before I continue? So in order to think about F2, what I want you to do is first let's just think about very long distances. So let's take q squared going to 0. So we're studying the electron interacting, say, with the proton at very, very long distances. So then what we have is we have this interaction vertex. So what is that? That's gamma mu F1 of 0 plus I sigma mu nu over 2m q nu F2 of 0. And what I want you to notice is that this interaction term looks like it comes from some sort of new interaction in the Lagrangian, which has the following form. So in particular, I remind you that our original interaction, i.e. gamma mu, came from the QED interaction, so that looked like E psi bar gamma mu psi, A mu psi, okay? So that's where the IE gamma mu interaction came from. Okay. And here I've just included the effect of that first form factor F0. And what does this next form factor look like? Well, it looks like it comes from a term E psi bar times sigma mu nu over 2m F2 of 0. And then you have a q nu. But what is q nu? Q nu is the momentum of the photon. And when you go from Fourier space to position space, each momentum becomes a derivative. So it looks like d nu a mu times psi. So in particular, this q nu has become a derivative acting on A. And I remind you that this sigma mu nu was antisymmetric in its two indices. So really, instead of d nu a mu, I could write d nu a mu minus d mu a nu, which is otherwise known as the field strength F mu nu. Okay. So F2, the second form factor, leads to what looks like a new sort of interaction between an electron and a photon. So this term here is familiar. This is the usual term that tells you that an electron has a charge. Okay, it's the Coulomb interaction. But here we have some sort of new term. And I'd like to spend a minute analyzing that in order to understand exactly what effect this term has on the equations of motion and on the dynamics of an electron. Before I do so, let me pause and see if there are any questions. No questions? Those of you who've studied the Dirac equation in a quantum mechanics class may have actually seen this before. You may not have seen it in this language, but for example, very often when people study in sort of, say, graduate quantum mechanics classes, when they study the Dirac equation, they'll look at the effect of this term. It's actually quite famous. Good. So in order to understand the effects of this additional term on the dynamics of the electron, let's look at the equations of motion which follow from this Lagrangian. So what is the equation of motion for psi? Well, let me just write it down. Okay. So you get the usual Dirac equation coming by varying this term. So we're varying with respect to psi bar here to get the psi equation of motion. So we have an E A slash F1 of 0 coming from this term here. And then we just get this term giving you a contribution that's E over 2m F2 of 0 F mu nu sigma mu nu, all acting on psi is equal to 0. So this is the usual Dirac equation. This is the correction due to the presence of the coupling between the Dirac spinor and the electromagnetic field. And this is some new term that will arise once we consider quantum corrections. Good. Questions? Okay, well, Dirac equations are sort of hard to look at and understand intuitively. So I'm going to do what we usually do when we see a Dirac equation and don't understand it. I'm going to square this Dirac equation to turn it into a Klein-Gordon equation. And then remember that the Klein-Gordon equation is basically the Schrodinger equation. And so we'll be able to understand a little bit more physically what these terms mean when we square this and think about it as a Schrodinger equation. So in particular, what I want to do, and this is just a trick, it's a trick that we've used a few times before in this class, is I want to essentially square this Dirac operator. But instead what I'm going to do is I'm not going to exactly square it. I'm going to multiply it by this thing, but with a plus sign in front of the m plus E over 2m F2 of 0 F mu nu sigma mu nu. So I'm just going to act with the Dirac equation on this operator. And I've chosen that operator very carefully so that the cross terms cancel. Okay? So just like if you take a complex number and you multiply it by its complex conjugate, where you change the sign of the I, you get the sum of the real part squared plus the imaginary part squared. Here we get I d slash minus E A slash F1 of 0 squared minus that second quantity squared, m plus E over 2m F2 of 0 F mu nu sigma mu nu quantity squared. All acting on psi is equal to 0. So now what I want to do is simplify this equation just a little bit. Okay. So let me start by looking at this term here. Okay. So this is I d slash minus E A slash. Okay. Just to make my life simpler, what I'm going to do is I'm going to let E hat be E times F1 of 0, because that is the effective electric charge. It's the thing that you would measure if you were doing an experiment, if you were measuring Coulomb's law. So just to make my notation simpler, I'll just incorporate that F1 naught squared of 0 squared into E. So what is this guy? Well, let's just write it out explicitly. This is I d mu minus, let's see, do I have a factor of I d mu plus E, sorry, I guess I need a minus E a mu times I d nu minus E a nu times gamma mu gamma nu. But what is gamma mu gamma nu? Gamma mu gamma nu, I could write that as 1/2 the anti-commutator of gamma mu gamma nu plus 1/2 the commutator of gamma mu gamma nu. So that is equal to, so let's first look at the anti-commutator. Well, the anti-commutator just gives you this operator squared. Okay? So that's the usual Klein-Gordon operator in the presence of an electromagnetic field. And then the second term has an anti-commutator. And what is the anti-commutator of? So that means you need to look at the anti-commutator between these guys. You know, you need to pick out the anti-symmetric part between these guys. And so you'll get an I over 2 times the anti-commutator of gamma mu gamma nu, which was sigma mu nu. And then you need the anti-commutator, or sorry, the commutator between these two operators, right? Because you're picking out the part that is anti-symmetric in mu and nu. And what is this anti-commutator here? Well, sorry, what is this commutator here? The commutator between two partial derivatives is 0 because of the equality of mixed partial derivatives. The commutator between a mu a nu is 0 because a mu a nu minus a nu a mu is equal to 0. So all you get is a factor of the electric charge times d mu a nu minus d nu a mu, otherwise known as F mu nu. Okay. So let's put that all together. And what do we conclude? We conclude that our Dirac spinner obeys a version of the Klein-Gordon equation, which looks like this. So I d mu minus E hat a mu of 0, sorry, a mu squared. Here, I'll just write it out. In my notes I wrote my F1, so I'll just write out that F1. So a mu squared, and then we have minus m squared. Expanding out this term here, we can then look at the term that is linear in F2 of 0, and so we get plus E over 2 times sigma mu nu F mu nu, and we get two terms. We get a 1 coming from this term right here, okay, because we have a sigma mu nu times F mu nu here. And then we get F2 of 0. And then there are other terms involving sigma mu nu F mu nu squared, which are going to be higher order things that we're going to neglect. Okay. The important point here is that this term here is the usual Klein-Gordon equation for a particle in a magnetic field, or a particle in an electromagnetic field. In particular, remember in quantum mechanics, how do you describe the coupling of a particle to a magnetic field? You replace p mu by p mu plus a mu. Right? That's the usual rule for describing the coupling of a particle in a magnetic field. And that's exactly what this term is here. And this describes some sort of new interaction between our particle and an electromagnetic field. In order to understand this a little bit more clearly, what I want to do is let's just consider our electron in a constant magnetic field. And let's work in the Weyl representation where we can write out explicitly what that matrix sigma mu nu is. In particular, we worked it out earlier on in the semester. Because we have a magnetic field, we only have an Fij, and so we only need sigma ij, and what was it? It's epsilon ijk times sigma k in the upper left and lower right corners. Or maybe it's upper right and lower left. I can't quite tell. So what does that mean? That means that in this particular case, this interaction, this equation, what does it look like? Well, it's I d mu minus E F1 of 0 a mu squared. That's the usual equation for a particle in a magnetic field. There's a mass term, and then there's a correction term proportional to 1 plus F2 of 0. And what does it look like? We have B dot sigma 0, 0, B dot sigma acting on our four-component field, which in the Weyl representation is just two two-component spinners on top of one another. And I want you to remember that in the non-relativistic limit, these four-component spinners that we're talking about that would describe the electron become a usual non-relativistic two-component spinner on top of a two-component spinner. So what we're doing here is we're looking at a correction to Schrodinger's equation for a spin 1/2 particle that looks like B dot sigma. Okay. So in the non-relativistic limit, this is a correction to the equations of motion proportional to B dot sigma. Okay. Now, if I handed you a Hamiltonian, a quantum mechanical Hamiltonian, and said, well, it's the usual Schrodinger operator plus a term that looks like B dot sigma, you would have a name for it. You would call it a magnetic moment. So what does this mean? So B dot sigma, so if you put a particle, let's put it this way, the B dot sigma term describes the interaction of a particle with a magnetic moment. Just to say that in somewhat different terms, if you have a particle that has an electric charge and is just sitting still, and you turn on a magnetic field, the energy doesn't change, right? Magnetic fields only, you have to take a charge and you have to move it around if you want to get it to interact with a magnetic field. If it's just a charged particle, right? Because of the Lorentz force law, F is, what is it, B dot V cross, something like that, I don't remember. But there's a velocity in there somewhere, V cross B. So if you have a particle that's charged and you turn on a magnetic field, nothing happens if that particle is just sitting there. But if the particle has a magnetic moment, that's like a little vector attached to the particle, and then the Hamiltonian, the interaction Hamiltonian describing a particle with a magnetic moment is B dotted into the magnetic moment. Okay. So what is this saying? This is saying that in quantum electrodynamics, electrons have an intrinsic magnetic moment. And in particular, it's proportional to sigma. What is sigma? Sigma is the spin of the electron. So the magnetic moment of an electron in quantum electrodynamics is proportional to its spin. I mean, this is an incredibly important thing that we've observed about quantum electrodynamics. It's kind of amazing, actually. I mean, it's worth stepping back and thinking about what we started with here. We started out trying to describe a particle with spin in terms of 4-component spinners. And then we coupled it to electromagnetism. And we discovered the only way to describe a particle with spin is to use 4-component spinners. Then we coupled it to electromagnetism, okay, in the only way that's possible, consistent with gauge symmetry, consistent with our symmetry principle. And what did we find? We find that there's an interaction term that tells us that an electron has an intrinsic magnetic moment. It's not just a part in quantum electrodynamics, in the theories that unify quantum mechanics and special relativity, it's impossible to write down a theory of an electron that doesn't have an intrinsic magnetic moment. So let me just let's just think about that for a second. Okay. In particular, what we see here, so the typical way that we characterize a magnetic moment is as follows. So you typically, remember the interaction of a particle with a magnetic field due to its magnetic moment is B dotted into the magnetic moment. Okay. So usually, that would be, something like B dot mu. So we usually characterize the magnetic moment, so the coefficient of the spin here. We usually pull out a factor of E over 4m. Okay. That's just, some sort of convention. And characterize the magnetic moment in terms of a dimensionless number that's known as G. It's called the Landé G factor. This is a convenient way of packaging the magnetic moment of an object. So for example, if you just took an infinitesimal point, like in Coulomb's law, G is equal to 0. A charged particle has no intrinsic magnetic moment. Okay. That is, however, if you looked at a sphere with a constant charge density, so what is a sphere with a constant charge density? Well, it has some charge, but if you give it some intrinsic angular momentum, it will also have a magnetic moment, because those charges are now moving. And if you take a sphere with a constant charge density and you spin it, then the magnetic moment will be proportional to the spin of the sphere, to the angular momentum of the sphere. And the magnetic moment will have a G factor of 1. So that's a nice normalization. Okay. So in quantum electrodynamics, what do we see? We see that the Landé G factor of an electron Well, I pulled out a factor of 4 here, and there are some factors of 2 up above. So the Landé G factor for an electron is 2 at leading order, not 1. And at subleading order, it's 2 plus this form factor F2 of 0. So, first of all, before we even think about this form factor, the fact that you got a 2 here is incredibly interesting. This is, I think, this is Dirac. So the fact that an electron has a magnetic moment proportional to its charge with a coefficient of 2 was an experimentally observed fact that nobody knew how to understand. And it was really Dirac who discovered that it was a consequence of special relativity. In particular, what we see is that when you try and write down a theory of an electron interacting with photons consistent with special relativity, that constrains the possible form of interactions. And in particular, it tells you that at leading order, the Landé G factor, describing the magnetic moment of the electron, has to be equal to 2 rather than 1. So this is telling you something about the microscopic structure of electrons in quantum electrodynamics. So one of the things that you know about electrons is that they have charge and that they have spin. Okay. What's something that has charge and has spin? Well, a sphere with constant charge density that's rotating has a charge with spin. Okay. So you could imagine in your mind, maybe electrons are just sort of little balls of constant charge density that are rotating. What you see here is that that is actually wrong. That's off by a factor of 2. This factor of 2 is telling you that the microscopic theory of electrons are not really just little balls of constant charge density that are rotating. There's something else. And this prediction of the Landé G factor being 2 is a prediction of, let's say, tree-level or classical quantum electrodynamics. And we now see here exactly what it is we need to compute in order to understand the corrections to the magnetic moment of the electron. So in particular, whereas F1 described some sort of momentum-dependent correction to the electric charge, F2 now has a natural physical interpretation. It is the momentum-dependent correction to the anomalous magnetic moment, or to the magnetic moment of the electron. And it was the calculation of this magnetic moment of the electron that I think was the first real signature triumph of quantum field theory. That's what I'm going to describe now. I'm not going to go through all of the details of the computation, but what I'm going to do is set up the computation using the tools that you've already learned, and then give you a sort of brief preview for how the computation will go. But before I do so, let me pause and see if there are any questions. Yes?
Are there any simple moving charge densities that would sort of give you a little bit of intuition for?
Yeah, I mean, you could certainly imagine, say, you could certainly imagine that you have a charge. So if you take a sphere with constant charge density and you spin it, you'll get a magnetic moment proportional to its spin with a G factor of 1. If instead you took a shell of sphere with the charge distributed all on the outside of the shell, you would get a different G factor. You would get a larger magnetic moment. I don't actually know if it's 2. It's probably not. I probably would remember it. It probably would say that in all the textbooks if it was 2. I don't actually know. Someone with a computer, look up what the G factor of a charged spherical shell is. Google G factor of spherical shell. Okay, tell us what the answer is. It's probably not 2. I bet it's bigger than 2. I don't know. It's a good question.
You have to engineer it somehow.
Yeah, right. You might be able to engineer it so that you get exactly 2. Yeah. Good question. And so somehow that's teaching you something about the structure of an electron. And indeed, that's just at Q squared equals 0. At higher energy, of course, there's a whole function's worth of data. Roughly speaking, as you go to higher and higher energy, you're probing more and more at the short distance structure of what an electron looks like. You could imagine doing an experiment, people do these experiments, where you do things like actually study F1 and F2 as a function of Q. And then what are you doing? You're studying the detailed microscopic structure of what an electron is. So what we're going to do here is just one computation, or at least part of one computation of this magnetic moment. Okay, good question. Any other questions? Okay. Okay, so let's compute it. Now, at tree level, of course, F2 is equal to 0. So this is going to be some sort of quantum correction to the magnetic moment of an electron. So let's work at one loop. And let's imagine, so what's the name of the game? The name of the game is to compute this interaction here. And so at one loop, well, what do we have? We have the tree level piece, which we've already discussed. That tree level piece gives you F2 is equal to 0, so it gives you the magnetic moment has G is equal to 2. Okay. And then you'll have various quantum corrections. Now let's work at the one loop level. Okay. So we're adding interaction. So you could add an interaction that looks like this. Okay. So that's one interaction that you could add. This is so this guy here is proportional to E. This guy is proportional to E cubed, right? Because I've added two more interaction vertices. You could also have something where you have, where you have a loop correction that looks like that, or a correction that looks like that. Okay. Finally, you could have a correction that looks like this. And then they'll be higher order. So what I've written here are the four interactions that arise, the four diagrams that can contribute at order E cubed. Yes? Oh, I'm sorry. I am not drawing this correctly. Oh, shoot. Sorry, I was drawing these diagrams thinking about scalar quantum electrodynamics. Of course, an so, yeah. Yeah, sorry. I mean, you get, I should have been more careful. What you actually get are tadpole diagrams, which of course we already argued don't contribute. Sorry about that. When I was thinking about drawing these diagrams out, I was about to neglect them anyway, but when I was drawing these diagrams out, I was thinking about scalar quantum electrodynamics.
Can't have a U that pops off the side and comes back into the bottom.
Sorry, you're thinking about, what are you thinking about?
Take the first leg and just like add a little horseshoe on it.
Yeah, you can have something like that. Good. Perfect. Perfect. Sorry about that. Good. Right. Thank you. Sorry about that. I knew I wasn't crazy. Well, not about this. Good. Sorry about that. Okay. So these are various diagrams that can contribute at order E cubed. However, let's think about these various diagrams. Okay. So if you looked at this diagram, you really wouldn't think about that as a correction to the electron propagator. You would think about that as a correction to, sorry, you wouldn't think about that as a correction to the electron vertex. You would think about it as a correction to the photon propagator. Similarly, these terms here, you wouldn't think about them as corrections to the interaction vertex, but rather as a correction to the electron propagator. It would correct, for example, the mass of the electron, not its charge. So these three terms here really are corrections to propagators, not to interaction vertices. And indeed, next semester we'll spend a fair amount of time thinking about what these propagator corrections mean, how to incorporate them into our theory, and so forth. Instead, what we're going to do today is focus just on this final correction, which is the only one which is a genuine correction to our interaction vertex. So what I'm going to do is I'm just going to write out this interaction for you and describe to you in a little bit of detail how this Feynman diagram is computed. Okay. So let me just remind you. Okay, any questions before I continue? Sorry I wrote those diagrams wrong. You know, like I often say, it's very hard to give an 80-minute lecture without saying something completely incorrect at least once. So I've gotten that over with. So hopefully everything else is right. Good. Any questions? Okay, so let me just remind you of the setup. So we have an incoming electron of momentum p, an outgoing electron of momentum p prime. You have your photon has momentum q, and I'll give it a, so let's give this a mu index. And then just by momentum conservation, you can determine 2 of the 3 momenta running around in this loop. So if you call the momenta of this guy k, then this has a momentum k minus p, and this has a momentum, what is it, q plus k. So you can now just go ahead and use your Feynman rules to write down this Feynman diagram. So you get 3 factors of IE coming from the 3 interaction vertices. You have an integral over the undetermined momentum, k. Then you have to start writing down the various, you have to start writing down the various interaction terms and propagators in this Feynman diagram. So let's first start, well, you have a photon propagator. So you have a photon propagator here. What is the photon propagator? It's minus I, G. Let's give some names to those indices. Let's call that an alpha index. And let's call that a nu index. So it's minus I, G, nu alpha over the momentum k minus p squared. Now we have to work out the various polarization structures. So you have a u bar of p prime. So as usual, we're contracting the fermion, the spinor indices along the arrows in the Feynman diagram. So just tracing along the arrows, starting with the u bar coming from u bar of p prime. We have a u bar of p prime, a gamma alpha, which is that interaction term. Then we have the propagator of this guy, which is q slash plus k slash plus m over q plus k squared minus m squared. You have a gamma mu from this interaction vertex here. You have, sorry, and there was a factor of I here from the propagator. You have another factor of I k slash plus m over k squared minus m squared. And then you have finally from this interaction vertex here a gamma nu, and all of that multiplies the polarization u of p. Sorry, I couldn't quite fit it in there, so there's a u of p there. Okay, so this is our first example of a loop diagram in this class. So far we've studied only tree diagrams. And in principle, it's now a straightforward exercise, emphasis on the in principle, to go ahead and actually just compute this. Okay. So next semester we'll learn all of the various tricks that one needs to do in order to compute this loop diagram. But in principle, it's something completely straightforward. Okay. It's an integral d4k of some function of k, and we could compute that k by working out the various, working out this integral and sort of simplifying it. There's all kinds of tricks that one could use to do that. I don't know how many of those tricks I want to describe. So maybe let me just pause here and make sure that everything is completely clear, at least as far as where this expression came from. Are all of the spinor indices and their contractions and all that stuff clear? Good. I'm trying to decide how much I want to do. So, I mean, there's various, so one of the things that I'll comment on is that one thing that's not at all obvious is that, so the claim that I made at the beginning of class is that this diagram takes the form of gamma mu times something plus sigma mu nu q nu times something else. Okay? One of the things that is not at all obvious from the expression that I've written here is that it actually takes that form. Okay? And so there's a bit of a calculation. You have to do some algebra. You have to manipulate some gamma matrices in order to show that. Okay? So for example, if you look at this quantity here, what do you have? You have a u bar, you have a u bar of p prime times gamma alpha q slash plus k slash plus m, gamma mu k slash plus m, gamma alpha u of p. Okay, so you have a product of, let's see, 1, 2, 3, 4, 5 gamma matrices inside, sandwiched between a u and a u bar. And then you can use various gamma matrix identities to simplify this. And indeed, if you do that, what you'll find, in fact, some of those gamma matrices identities you proved on one of your problem sets. But what you do if you find that is you get something like u bar gamma mu, so u bar of p prime times u of p times some stuff plus u bar prime u times q mu times some stuff plus u bar of p prime sigma mu nu u of p times q nu times some stuff. Okay, so that's a reasonably straightforward calculation. And one of the things that I claimed for you was that by the Ward identity, whatever you get that's proportional to q mu has to be equal to 0. That was a consequence of gauge invariance. And when you calculate all of this stuff out, what you'll find is that the stuff that you find here precisely integrates to 0 when you do the integral d4k. Whereas the stuff that you find here and here actually does not integrate to 0. I don't think I want to go into too much detail just because this is, just a calculation and it's something we'll spend a lot of time going through next semester. But one comment I'll make is that when you actually do this calculation right here, what you actually find is an answer that is divergent from the integral d4k. In particular, this is an integral d4k. But the thing that you're integrating, so an integral d4k, whether it is divergent or convergent depends on the behavior of the integrand at large k. Okay. And if you look at the integrand here, you see that you have 6 powers of k in the denominator and 2 powers of k in the numerator. And so that means that at large k, it's like an integral d4k of 1 over k to the 4th, which is typically going to be logarithmically divergent. It's like an integral dx over x that diverges at x goes to infinity. Here you have an integral d4k over k to the 4th, which is going to diverge at k goes to infinity. Okay. This is one of the famous divergences in quantum field theory. And one has to develop a theory in order to deal with these divergences, and that's the theory of renormalization. But from a very practical point of view, you can understand precisely at this point what it is you should be doing with this divergence. In particular, let's remember what the physical interpretation of this term was. What was the physical interpretation of this term? Well, it's a contribution to the electron vertex proportional to gamma mu, okay? Otherwise known as the electric charge. That means that if you found a UV divergence here, that's not something that is physically observable. Okay? Because what you actually measure in an experiment is an electric charge. And, well, I think that I don't want to go into too many details, but the basic point is that any divergence that arises in this calculation, you would just include as some sort of divergent contribution to an electric charge. And really, the right way of thinking about this divergence is, the right way of thinking about this divergence is that the parameter E that appears in your Lagrangian has nothing to do with the actual electric charge that you measure. Okay? Because what is the parameter E that appears in your Lagrangian? Well, it's some parameter that appears in your Lagrangian. You don't ever actually measure it. What do you actually measure? You measure something like Coulomb scattering. Okay? And if you actually were to do an experiment where you measured Coulomb scattering, you would get the E that appears in the Lagrangian along with this infinity that appears from this diagram. And so the actual value of the electric charge that you would measure already includes that infinity in it. This infinity only ever arises because you have decided to write quantities in terms of naive things that are parameters in Lagrangian rather than actual physical quantities that you measure. And if you went ahead and you rewrote all of these expressions in terms of physical things that you measure, all of the infinities would cancel out. Okay? Let me say that a slightly different way. Okay? A slightly different way of saying that is that you could get a UV divergence in this calculation, but what you're calculating here is not something that you, strictly speaking, measure. The thing that you actually measure would be, for example, the comparison between two different calculations. Like when you, so for example, this divergence that you would encounter when you did that integral d4k is something that would appear in the definition, in the relationship between the electric charge that you measure and some parameter that sits inside a Lagrangian. I mean, if you wanted to think about it a little bit more physically, you could think about this picture of screening here, okay, where you would start with then this, the electric charge of the proton before you've screened it out is, basically infinite. And it's only after you screen it that you get by an infinite number of electron-positron pairs that you get down to something finite. Okay, so next semester we're going to understand in a lot more detail, the theory of renormalization and how we deal with these apparent divergences in Feynman diagrams. But the point to remember is that they only ever appear when you write things in terms of unphysical quantities. If you write things in terms of physical quantities that you measure, all of these divergences always go away. But the thing that I wanted to discuss today is the computation of this term here. The important point, and the reason why it's something that is a relatively easy calculation, is that this guy is actually convergent. No renormalization is needed in order to calculate this quantity. The reason being that whereas naively this integral goes like an integral d4k of something that goes like 1 over k to the 4th, you've pulled out a factor of a momentum here, okay? And so that means that you need to have an analogous factor of momentum in the denominator. So this is something that actually goes like the integral d4k of 1 over k to the 5th, rather 1 over k to the 4th, just by dimensional analysis. And so it's a totally finite integral, okay? And one can just do it. We don't have quite enough time to do it now. But if you do it, let me just tell you the answer that you get. The answer that you get is an expression for F2 at q equals 0, and which is e squared over 2 pi. So it's one of these cases where you have a very complicated set of intermediate steps, but a very simple answer. Or putting this back into our formula for the g factor, this is 2 plus alpha over pi. Or putting in our numbers, alpha is about 1 over 137. This is a correction to the magnetic moment of the electron that's, of order a couple parts in 1,000. And this is, one of the most celebrated checks of quantum electrodynamics. Just for the sake of, just for fun, in fact, it turns out that the magnetic moment of the electron is perhaps the most well-measured physical constant. Let's see if I can get 319. Most well-measured, most accurately measured physical constant in nature. So it's known to have ordered 10 digits. So that last digit is, plus the last digit, there's a 7 plus or minus 3. Okay? So this is the experimental value of the magnetic moment of the electron. You can see that, what we've done here is we've calculated the first correction. But in fact, you can actually use quantum electrodynamics to study higher order diagrams. I think, okay, let's see if I can read what I wrote here. So the theoretical measurement matches the experimental measurement. Unfortunately, I didn't actually write down what the errors on the theoretical measurement are. This follows from a for-loop calculation in quantum electrodynamics. In fact, I think it's been done at 5 loops. Okay, I think when I looked this up a while ago, and so I think it's actually been done there. At least certain terms have been done at 5 loops, but it's probably the most impressive match between theory and experiment in the history of physics. I'll make a couple of comments on the theoretical as opposed to the experimental values of G-2 for the electron. One of the comments that I'll make is that at leading order for the QED calculation that we made, that we did above, we only took into account the theory of electrons and photons. When you work at such a high degree of accuracy, you actually need to include all other sorts of interactions in order to correctly get the G-2 of the electron. You have to include all sorts of other kinds of virtual particles that can appear. And so in order to correctly theoretically compute the magnetic moment of the electron in quantum field theory, it was really necessary to use all sorts of different kinds of particle physics. So for example, details of parton distribution functions for the nucleons and things like that entered into this calculation, this theoretical calculation of the magnetic moment of the electron. So there's actually a great deal of physics that goes into this computation, not just the quantum electrodynamics that we've described above. The other comment that I'll make, which is in some ways a more interesting comment, is that I wish I'd remembered what the error bars were on this theoretical computation of G-2, because the theoretical error bars are actually larger than the experimental error bars. And interestingly enough, it's sort of fun to ask where the theoretical error bars come from. The theoretical error bars come because we're doing a for-loop computation, which means that you're doing a 16-dimensional integral. And the primary theoretical error bar comes from the fact that we don't know how to do that integral. Okay? And in fact, the way that people compute this is by doing numerical Monte Carlo simulations of these integrals. They're highly non-trivial integrals. They're hard to do. And in fact, I just think it's sort of remarkable that the largest error in this match comes from the fact that we don't know how to do an integral, rather than from a fact that there's some sort of essential physics that we don't understand. Okay, so I actually had prepared a sort of more detailed computation of this F2 of 0, but I think it's probably best for me just to stop there and see if there are any questions.
Shouldn't we have a factor for the photon of that formula, like epsilon of q?
Yes. So what I'm doing here is I'm doing mu. So in particular, I should really have put an epsilon mu here. if you wanted to have an external photon with some polarization.
Okay.
Or, you could also imagine, the reason why I'm not putting in that polarization there is that you could also imagine this as a contribution to some other process, like the one that I wrote down here, where it's an internal photon rather than an external photon. That's really how I think I want to think about it in my head, though. Yeah. Good question. Yes.
So there's because it's 3/5.
It's 3/5.
3/5.
G.
Point. Yeah.
Point.
G1.
Wow, the G factor is smaller for a spherical shell?
Or, yeah. This is,
Oh, I see. Okay. That's interesting. I'm kind of, no, I'm actually, okay. So the statement is that for a spherical shell, if you rotate it, the angular momentum over the magnetic moment is 3/5 instead of 1. I guess that's partly because the mass is also now distributed. Because the Landé G factor, we divide it out by a factor of the mass. So it also depends how the mass is distributed. Okay. So it's not actually bigger for a spherical shell. If you imagined that the mass density was in the interior, but the charge density was on the exterior, then I bet you could get G bigger than 2. Yeah. Okay. Anyway, thank you. Yeah, it would be sort of fun to look up what it is for different sorts of configurations. Good. Any other questions? Good. Okay. Thank you. See you all next semester. I hope you're going to register. Are you guys registering for this course? You should all register for this course. It'll be fun.